Hey there, everyone. My name is Ryan Schewel. Welcome to my analytics channel here. So, in the in the narrative today, I want to talk about urban heat islands and how can we detect this and use this methodology or this technique to understand how we can plant trees in a way that is going to benefit the environment, the local environment, and a greater environment to the greatest extent possible. So, basically, what is an urban heat island? It's a metropolitan area or greater metropolis area, if it's a few different megacities, that basically comprises of a significantly warmer than surrounding rural area due to human activities and the infrastructure of the local area. So this phenomenon became known probably within the last 100 years or so. It's been around for a while. It's been on people's radars for quite some time. But basically, because of extreme building, roads, bridges, traffic. Okay, so buses and taxi cabs and people driving cars and just people expelling, emissions into the environment through heating of buildings in the wintertime, running AC in the summertime, and things like this, right? So the local area has become basically an island or an epicenter of higher temperatures, and this can be pretty significant, anywhere from a couple degrees up to maybe 10 degrees warmer than the nearby natural areas, especially at night. Okay, so the heat island tends to retain its heat, and the urban areas tend to dissipate its heat 10 degrees centigrade, due to the natural activities of plants and trees absorbing carbon dioxide, right, and emitting oxygen for us to breathe. So we can easily create a spatial risk scoring system to try to understand and detect hot surfaces, hot neighborhoods, and rank these spaces. And then, based on this information, use this knowledge basically to understand where we can plant trees to help the greater good of the community, right? To create more oxygen for the local area, cooling effects for the local area, and try to dissipate the heat from this urban heat island. Okay, so let me jump into it and I'll show you what I mean. Okay, I think this is a pretty cool analysis. I hope you agree. I hope you can follow along. And if you have any comments, by all means, put those into the comment section. Hopefully, they're positive comments and not negative. And go ahead and subscribe to this channel too if you think it's going to help you to learn and to become educated and to become more knowledgeable about analytics practices in the near future and in the distant future too. So I'm going to look at the 5 boroughs of New York City. We have Manhattan, Brooklyn, Queens, Bronx, and Staten Island. So I have all the boroughs here. I'm going to list these literally into a list right here. And this is going to create a bunch of polygons for me. A polygon is a multi-sided object, right? Not necessarily a square or a rhombus or a trapezoid. It could be many different sides, like an octagon, hexagon, but it doesn't have to be any of those, right? Poly just means many-sided shape. So I've got right here Manhattan, Brooklyn, Queens, Bronx, Staten Island. This is my list, and I have recognized about 2,060 parks, either smaller parks or larger parks. Central Park is probably one of the largest, might be the largest. I didn't actually measure the square area of all these parks, but from small to big. Okay, so we're going to cover the whole gamut here. So I'm getting all this information, by the way, from here. We have geodata frame, and I'm concatenating boroughs, right? And we have OX geocode. So this is pretty interesting. You can go ahead and do some research. I have gotten into this stuff kind of recently. I'm still learning about how this works too, but this is pretty fascinating. They have all kinds of relevant data about area, borders, boundaries, things like zip codes, natural separation areas between different geographical regions, different zip codes, different state boundaries, whatever. What else is there? There's FIPS codes, so all kinds of interesting things. So I'd encourage you to take a look if you are curious about this. Okay, so I'm going to go ahead and get NYC boroughs and parks. Okay, and I'm going to pull that from a public data source that's going to give us all kinds of information about XY coordinates, X and Y being the latitude and longitude coordinates, and we're going to create hexagons so we can see the basic area of each of these plots and then understand what is the urban area or the industrial, the developed area versus the natural nature area. Okay, So we have all of the shapes of hexagons, the hexagon being probably the most perfectly designed shape in nature. This is how bees build their honeycombs. It's in a hexagonal shape with 6 sides, and that's supposed to be the most efficient structure for creating anything, right? So nature has figured this out. Humankind is trying to figure this out right now. They're trying to model what bees have been doing for millennia, okay? So we're going to go with the hexagon shape, and I'm looking at hexagon cells in New York City, about 5,322. Again, to render the borders of the city, the image, plot all the hexagons so we can see the urban area and the natural area. And we're going to look at the delineation between these 5 boroughs too, okay? So each borough is going to be separate and distinct from the others, and it's going to help us understand the effects of the urban heat island, and then the benefits of creating more trees. And again, the goal here is to find the optimal places where we can plant trees to try to offset some of the destructive, um, not benefits, the destructive implications or impact of creating an urban heat island. Okay, so that's the goal here. So we're going to loop through all the different items here of the geometry and of the index. So this is 2 loops. We're looping through index and geometry. So basically looping through all the rows and all the columns of this geological matrix right here. And we're going to go ahead and create the head of this hexagonal formed shape that we're creating right here. So I want to go ahead and look at that. We should see it pop up in just a moment here when this runs. It's probably finish off in a couple seconds here. I think this one is quick. Some of these do take quite a while to run, but as I recall, this one was relatively fast. So let's see how it goes here. Maybe it will take a few minutes. You know what? I'm going to hit the pause button. I'll join back when this finishes up. I don't expect you guys to sit and wait for this thing to finish off. I'll let it go, and then I'll resume the recording when it's all done here, okay? All right. So our data frame finished off, and it looks pretty nice. This is what we end up with right here. So we have these headers over here. I'm looking at boundary box. So this is the hexagon shape, the north, south, east, and west, the place ID. This all comes from over here, like the hexagon and the borough 357 data, OSM data from GDP overlay, right? So everything is consolidated into this one nicely shaped data frame. So boundary box, OSM, longitude, latitude, and longitude coordinates for all these locations around the 5 boroughs. That's what we're focusing on in this case. So we have place rank. The type is city, neighborhood, park, island, things like this. Place ranking shows the rank of the place from the most high, the coarse country, which is kind of spread out, kind of higher number, to finely defined buildings. So everything is sort of structured into a building human construct type of shape versus a nature shape. Geometry is the actual polygon or hexagon that we're looking at. In this case, these are going to be all hexagons. We have the address, city name, display name, and we also have geometry. These are the hexagons I just mentioned a moment ago, and the spatial cells. And we have, what else? Park area. If there's a park, how big is it? If there's no park, then there's nothing to quantify there. And then H3 or hex bin or UI intensity is urban heat island intensity. So how intense is this area that we're looking at in terms of this this hexagon, the shape? Like how intense is this shape versus other shapes around New York City, other buildings emitting, again, like creating emissions, fossil fuels, right? Creating this urban heat island that we're trying to analyze here versus more rural countryside, or at least park space in between the island spaces. Okay, so we're going to add a couple things to this data frame. We end up with LSTC and UHI intensity. Down here, after these 2 columns, we add 2 more columns, appending both columns to the data frame. So we have population density and vulnerability in terms of the concentration of the hexagons that we're mapping and that we're analyzing here, divided by the basically normalizing the population density. So we have population density in the numerator and population density divided by the maximum in the denominator, right? So if your maximum numerator and denominator are the same, then that's going to be a pretty large number, right? So it's going to be more intense. If the density is much lower divided by the maximum, then the relative metric right there is going to be lower, right? So we're just trying to take everything and normalize it so we can compare all these hexagons across New York City and the 5 boroughs in a uniform fashion, okay? So that that's that step. Then we get vulnerability. I think that's the last what we have, vulnerability. Yes, so now we take the next step and append a few more columns onto the data frame. So this is all called feature engineering. I talked about this in several of my other videos when you have your basic features in your data frame and you start creating new features and appending new columns onto the data frame based on the metrics or the quantifiable different elements that you are analyzing over here. So we're adding a few more features called feature engineering onto the current data frame. And this is going to give us population norms, UHI, in terms of heat index, urban heat index, vulnerability, how vulnerable are these pockets of heat indices, right? Like if you're in the middle of Times Square in the middle of summer, it's going to be pretty hot, guys. It's going to be boiling hot and probably unhealthy for the average person to be outside for any extended period of time. That is captured by vulnerability. And then tree potential. This is what we're trying to maximize right here. We're trying to understand where we plant trees across New York City, across these 5 boroughs, the entire area. Wherever we plant trees, what should be our priority so we can maximize the utilization of the reforestation of this urban heat island, right? That's the goal that we're trying to get to. So let's go to the next step here. We are going to add traces over here and look at the top hexagonal shapes, okay, in terms of the priority. I just showed you the population, what was the thing? Normalization, the population normalization, right, and how concentrated this heat index is. Urban heat index is UHI, population normalization, vulnerability normalization. Again, that's how hot or how not hot a certain area is. In terms of these hexagons that we're going to see plotted on the map in just a minute. We're going to take all of that, dump it into a Plotly chart. So pretty much all of my charts, as far as I know, maybe there's a couple of exceptions, maybe there's no exceptions. Basically, all my charts I use Plotly. I like it because it's interactive, it's dynamic. You put the mouse over it, the tooltip pops up. You can zoom in, zoom out. It's very flexible and scalable. I really like these plots a lot. There is a couple of downsides. I mean, it's a little bit harder to work with these things. It takes a while to get up to speed with how to create these plots. And if you make a mistake, there's not a ton of documentation out there. There's some good documentation, but not tons and tons that expose all the nuances of these Plotly charts. So it's really trial by error. You have to kind of figure it out as you go, see what works and what doesn't work, and just learn from your mistakes. And it is memory intensive, but like I just said, it's very dynamic, integrated, interactive, works seamlessly with JavaScript, and it makes a very dynamic, very powerful visual effect, right? That really pops off the screen, really jumps off the screen, and really communicates the message that you're trying to share with your audience, which is basically, what is this urban heat island that we're looking at? In this case, right, Plotly charts are used for all types of different things. Where is the urban heat island? Oops, I just saw a mistake here. Let me refresh this. What is the urban heat island? Whoops, that's weird. It's giving me a mistake. Let me go back here. Run all above selected cell. So that is going to finish. And let me run this one next. So again, where's this urban heat island? How do we plot it? And how do we understand the vegetation and the park areas and the natural setting within this heat island that we've created, right? That we call Manhattan, and the other boroughs that consist of New York City, right? So this could take a few minutes to run. Let me pause it, and I'll swing back here in a couple of minutes, okay? And we'll pick it up and where we left off in just a couple of minutes here, okay? Okay, so at this point, I'm done building the data frame. It looks pretty good. And again, we have the urban heat island, the population normalized, the vulnerability of these different spaces in terms of the hotness or the heatness, how vulnerable certain areas are to this EHI analysis that we're doing, and then the tree potential. Okay, this comes from the park fraction, which comes from Minimax 1, which links back to what we're getting from over here from this data. It gets a little complicated, guys, but try to follow along. It's super interesting. That took me a while to figure this out too, but it's worth it. Whatever time you put in, you get paid back, right? This is investment in education and fantastic learning opportunity. So it comes from over here, okay? So we have to trace back to here. All these GPD, all these GPD items, right, are free and comes from the Geo data frame. The PD, I believe, is Pandas data frame. This is a Geo data frame. So we get all this data for free. New York City, overlay it on a map. We have the data frame down here with the intensities, population density, vulnerability, right, in terms of the hotness of the space. And in the next step, we get tree potential. So is this a potential location to plant a tree, right? And we're looking at little tiny hexagonal shapes. We'll see that in just a minute. Tree priority. Okay, so the tree potential is 1.0, but it could be a percentage of that, right? Or a fraction of that. If we look at tree potential, yes or no, this has a potential for a tree. It says 1.0, but it's actually only 0.29%, 29% beneficial to plant a tree here, right? So this says 1.0. This is actually higher, slightly higher, almost 33% than this. So we'd rather plant a tree here as opposed to here. This is 29.6. So again, kind of low. This is 34% benefit for planting a tree there. This is 29%. So even if it says 1.0, we really want to look at the probability or the percentage of planting a tree and what's the payoff for that, right? So we want to look at a more granular level. So everything's coming together. That looks good. We can go ahead and plot the 10% tree planting priority blocks, okay? That's a tongue twister, I'll admit that, okay? So we can zoom in on the map here. These are the hexagons that I was speaking about before, right? When we were talking about hexagons. So this is what it looks like plotted on a map of the silhouette or the parameters here of Manhattan. All right, if I zoom out a little bit, we can see Queens. That's where I live, right here, just a little bit west of Manhattan. I mean, east of Manhattan. Then you see down south, this is Bronx, Staten Island over here, and this is the Bronx over here. So Bronx is the north, Manhattan is a little bit in the west, Queens is on the east, down south is Brooklyn, and then Staten Island is off here, hanging off down by itself. Looks kind of like the tip of the boot, right? If this is kind of like a boot-shaped map right here. Whoops, I was going to zoom out. Try to look at the boot a little bit. Maybe not. Okay, it's just using my imagination there, just trying to get creative. So a little bit like a boot, but not totally. So let's move on. Now we have the plot for the hexagonal plot, right? We can see the urban heat island, and we can see the parks scattered all over the place. So you can see Central Park right in the middle of Manhattan. Up in the Bronx, we see a couple of green areas. So those are parks right now. That might be a great place to plant a tree. But again, is that the ideal or the optimal place to offset the heat generated by the island of Manhattan and the surrounding areas of Queens, Brooklyn, Bronx, and Staten Island? Okay, so we're trying to find the ideal places. Of course, you can go plant a tree in Central Park. No problem with that whatsoever, but is that the ideal place? We're trying to figure out the optimal place to plant trees to offset the heat created by Manhattan and the surrounding areas. So let's hit Control-Enter here and run the next cell. So again, I'm looking at pretty labels. I want to see what this looks like when I print it out, just to have like a quick sanity check of what the data will appear like. And then we're going to loop through all of the items down here. So I is representative of the rows. We're going to loop through all the rows. Col is going to be the columns, and we have basically a matrix. So we're going to loop through all the rows and the entire matrix, loop through all the columns in the entire matrix, and look at the labels from all these columns and compare that to the population density. Okay, so if the population is super, super dense, maybe we can't plant a tree there, right? If it's less dense, maybe that is more of an ideal place to plant a tree. And of course, we're looking across all of the 5 boroughs of New York City, with Manhattan being one borough, not New York City. New York City is all 5, right? Manhattan is 1, Queens, Brooklyn, Bronx, and Staten Island to round it off. So we're looking at population density. Again, the rows represented by I, the columns represented by col, and the matrix is going to be the entire universe of all the rows and all the columns. So this is what it looks like when we look at the visual. So this is the north, south, east, and west box plots that we saw before, right? So nothing new there. And we see all the boundaries, all right, and the polygons. That might be a little bit too much information. That might be TMI, guys. I'm going to go ahead and comment that out. If you want to see that, I will leave that in there. Print hexes, print that. I'm going to comment that and rerun it. Okay, just so it's a little bit easier to look at the chart. We have tons and tons of information there. These are all the coordinates across the whole borough area. So lots of information. Some of it is very helpful. A little bit overwhelming too because it's almost TMI, too much information. Let me just assume that the data is correct, and there's no reason it shouldn't be. It came from those items that we're importing at the beginning, the GeoPandas data that's coming to us, all free, by the way, all free. We just have to fetch it and plug it into our model here. Let's just look at, I thought I just commented that. What the heck? Let me look at this. I just want to look at the plot of the map. So let me see, print. Did I miss one over here? Print hexes. So I think that. Okay, let me get rid of all these things. I'm just going to put a comment right there just so we can ignore that. And I think the map is done. Yeah, okay. So let me just get the map. Let me get rid of all those print statements. I'll do this one more time. Okay. And we should have something that renders all these hexagons across the borough area. We'll get rid of all the details behind that. We need that to do the plot, but we don't have to print that. When we print that, it gets a little bit overwhelming. You know, for most people, even myself included, I don't know everything about all the details of everything in the whole heat island universe, right? So I'm learning some of these things as I go, and just sharing my knowledge with you guys. That's how it works here. So that's it. But that's even a little bit too much for me. Maybe for the person that invented this, whoever that is, wherever they are, God bless you. Thank you for this free gift. That's awesome. But if you're not that person, maybe we don't have to see that. We already saw a lot of the evidence over here in these data frames right here. That's all evidence, 100% accurate, true. We validated that and that as well, and this one too. And I think that's the first one that we saw there. Okay, so I think that's fine. Say we have enough evidence. We don't have to prove this beyond a reasonable doubt. This was our 10%, top 10% tree planting area. Okay, and that is fine too. I want to get more details now. Whoops, I hit out. I want to go in a little bit. So we have more details coming up in this next view down here. Okay, and it looks like it's pretty much done, guys. Let me zoom out just a tad here. Just a little bit, shrink that down. Okay, so this is good. So it took a little effort, a little bit of labor, but we're in a good spot right now. So we have all the details. Before we got the top 10, right? So the top 10 hottest places in New York City. So anything that's not hot is not a hexagon. You can see there's a lot of activity just south of Central Park. This is Midtown right here, Midtown Manhattan. You have a little bit on the east side, a little bit on the Upper West. You have some stuff around Times Square, a little bit around Wall Street, not too much. That's not the top 10%, right? Wall Street. This is the top 10% of everything. But let's look at more of the detail. I don't want to filter out the top 10. I want to see everything in the borough area. So we can see the original parks over here in green and the upper right-hand corner of the map over here. We see some green over here. This looks like Queens, what was it called? Fleshy Meadows Park. I can see Central Park. That's the rectangle right in the middle. I can see Prospect Park down here in Brooklyn. There's a little bit more down here in Queens. Queens kind of like loops around Brooklyn. That's interesting. For the longest time, I thought JFK was in Brooklyn, but it's actually in Queens. So Queens has two airports, right? JFK and LaGuardia. And we can see all the urban heat island with darker concentration, showing closer to 1.0, so the most intense heat, and the lighter colors, kind of like a salmon pink down here at the end of Staten Island, the southwest corner of Staten Island. So that looks good. Let's choose the optimal tree planting locations. So we have done all the homework, all the effort, all the labor to lift this up and to get this into a good state. I think we're pretty close now to finding the ideal locations for planting trees. We are going to look at the top N number of trees per borough. We're going to go with 60. Now, this is completely arbitrary. You can say we're going to plant 200 trees. 60 probably isn't a whole lot. Although if there's zoning ordinances and compliance and regulations, a lot of red tape. Maybe just to get 60 trees planted is going to take a huge effort. I don't know. I'm just saying 60 to start with. If we have you know, open ticket, carte blanche. We can do whatever we want and plant 1,000 trees. You can easily bump this up to 1,000 and say, okay, let me find the top 1,000 areas to plant a tree. And we have the blessing from the new mayor, McDonough, I think is his name, McDonough, something like that. Um, and we can move forward with this. Then go ahead and plant 1,000 trees. Plant 10,000. Okay, God bless you for doing that. But I'm just starting with 60. It's an arbitrary number. Let's just see what we get with the 60. So we have priority flag index. So this, by the way, was what we had before. Tree potential, right? These are close to 1.0. Tree priority. Now this is going to be a fraction of this. So it should be kind of close. With this being rounded up to 1.0, this is going to be more of a probability for priority, right? Where can we plant a tree? Priority flag, these are all set to 1. So these are all trees that we should be planting right now. And we actually are ranking these too. So I actually set up a little ranking metric over here. And that comes from this right here. Rank method first ascending equals false. Okay, so if I put this all in one line, it's probably a little bit easier to read. I like to do it like this. So we have the ranking in descending order, right? So the number one most important tree to plant is literally at this longitude, this latitude. Okay, so I don't see it right here. I might have gone a little too fast. We should probably have like a street address, but that's easy. With geocoding, we can actually add in a street address. Or if this is a park and there's no street that goes like directly over lane, this longitude, latitude coordinate, we can get a very close approximate. We can do geocoding to get the street address. Let's take a quick look at this. Python. Okay, so here we go. I've used this library before. This will do it. So based on the latitude and longitude, print location.address, and we can get the raw address from any of these. So I did not do that step. I just occurred to me right now. I didn't do it before, but we can go ahead and append on the street address over to the right here. So we have the ranking of the trees. This is number one place that we should plant, number 2, 3, 4, 5, and so on and so forth down the list. I can add on one more column. I'm not going to do it now. But I just showed you the code. Just Google it if you want to add that in. That would be a good homework assignment for anybody trying to learn this stuff. Add that in, reference the data frame, which would be, let's see, location.raw. Okay, so this is the name of the location. I'm sorry, this is the name of the data frame, and address components equals raw address and print street address. Okay, so I don't think you need to print. You can print this if you want. This would take it and append that onto the data frame. Of course, you'd have to change the name of the data frame from location to tree sites. That's the name of my data frame. If you want the street address, just go ahead and append it on. I put a lot of time and effort into this. I'm not going to change it at this point. But then, yes, so there we go. So we have the borough, latitude, longitude. Here is the next step. I'll run this cell. This should finish off quick. Yep. Borough, lat, long coordinates, tree, priority. Okay, so these are going in descending order with the highest number close to 1.0, going down in descending order, and plot everything using Mapbox. Okay, so I think we have one more plot ready to go over here. Just like we saw before, GeoJSON comes from the hexagonal shapes. Those are all the free data sources that I fetched before. I showed you how that works. Color scales could be red. You can make this green, blue. Green might get a little bit confusing with the trees and all the parks. I think red or blue, maybe purple. Red, I think, is probably most appropriate because we're talking about heat. Heat is associated with reds and oranges, so I think that makes sense. If you make it blue or purple, it might get a little confusing. It might look cool if you're trying to represent something that's hot. So probably would just keep that as red. Let's look at the data frame right here. Everything looks to be on the up and up. Looks pretty crisp and pretty tight. We have the population norm, vulnerability. Remember, we normalize these a couple steps back. Tree potential, tree priority, going in descending order, right? So that's how we have the top trees down here in descending order. These are all in Manhattan. The ranking 1.0, and here's the centroid the point. This looks pretty much almost perfect, definitely in a good state. We're in a good spot right now to wrap this up. The only thing I would add, sorry, I apologize, I forgot to do it before, add in the street address. You can get that from your geocoding right over here. Okay, I think that is a good take-home homework assignment for everybody there. If you're really interested, go ahead and Google that. That should be pretty easy to do. Again, totally free. All these tools are free. Take a crack at it. If you can't figure it out, post it in the comment. I can swing back and offer a solution. But I think if you're trying to learn this stuff, that is a good way to just jump in, assign the street address. I forgot to do it. You can go ahead and pick up the slack, pick it up where I left off. I am going to wrap it up right here. That's how we do urban heat island analysis, detecting the hotspots, right? And where can we plant the trees that are going to have the most offsetting positive impact. You can see all of these green areas right here, right? And this is what I was talking about before with the plotly chart. When you put the mouse over it, it pops up the message, tree priority 0.806. These are all high priorities, 0.80, 0.9 something, 0.93, 95. These are where the trees should be planted. The light green kind of looks like a grassy color green. These are the existing parks. We can plant trees there. We already have a park. I don't think we need to add more trees. But if we have individual standalone trees or like a little strip of earth, and we can add a couple dozen trees in one city block, these are the top places to do it to offset the hot or the heating effects from the urban island. Okay, guys, so that is it. I'm gonna save my analysis right here. Let me just go ahead and hit the save button. Last checkpoint 3 hours ago. Let me update that to now. Hopefully it says now. Okay, let me get that updated. These things go slow. I get it. I'm getting kind of used to it, but not that used to it. Should probably just get a new computer and then I'll have to get used to it. So yeah, these things can go slow sometimes. I have no idea how long this is going to take to save down. Let me save it. I'll share all the code with you guys. I'll post the code when I post the video later today, like I do with all these videos. You have everything you need. Copy, paste it into your own Jupyter notebook. Okay, drop it in, and you are good to go. You've got everything you need right here at your fingertips. I'm going to wrap it up. Just try to get this guy saved down. If it will do what I tell it to do, that would be a miracle. And if not, then I'll figure out some alternate way to get this done. Okay, so I will give you the code. I will deliver the video later today. Thanks for your time, guys. Thanks for sticking through to the end. I love that. And I will see you guys when I post the next video. It should be a little bit later today or maybe tomorrow, so keep an eye out for that. And make sure to subscribe. And if you have comments, post those in the comment section. Thanks so much, and I'll talk to you soon. Goodbye.